Okay, we're looking at problem 12-68. It's an example. Well, reading the problem, it says the airplane lands at 200 feet per second on a straight runway, and it has a deceleration that's described by the graph right here. And if we look at it, that's an A versus S type graph. We want to determine the distance S prime traveled before its speed has decreased to 25 feet per second. And then we're asked to draw the ST graph. Now, in the solution that the author produced, we have the answer to the first part, determine the distance. The author didn't actually draw or compute the ST graph. We'll talk about how to do that, but we're not going to do all the pieces to that. So we'll deal with basically the first part of the problem. And noticing a little more closely our acceleration versus position. Our deceleration is a minus 15 until we hit a distance of 1750. After that, our deceleration is a minus 7.5 feet per second squared. So given an A of S graph, and again looking at our equation sheet, our best choice dealing with A and S, and the V information that we've been given is the ADS equal VDV. To answer the full question, we would have to make our way toward time. So let's start off with the ADS equal VDV form. And so let's zoom in a little bit on this. And so in the region where S is between 0 and the change point 1750, we were told that our initial velocity was 250. And we can decide that S is equal to 0 at that point. Okay, using ADS equals VDV. On the V side, we'll simply put VDV. On the ADS side, A becomes minus 15, the DS here. Integrals on both sides of the equation. On the S side, our limits will be S values, starting from an S equals 0 initial condition to an S equal indeterminate, just an S value right here. That may be a little bit hard to see, and I can probably zoom in just a touch more. Okay, and so that is an indeterminate S limit. Now, at time equals 0, our lower limit here has to be velocity that corresponds to S equals 0, and that was given as an initial condition of 250 feet per second, and integrating the VDV to an indeterminate V. Integrating VDV gives us a V squared over 2, evaluated at the limits between V and 250, upper limit V, lower limit 250, and integrating minus 15 ds gives us a minus 15s, evaluated between the upper limit of S and a lower limit of 0. Plugging in the upper and lower limits gives us and we'll have a V squared on this side. We'll take the square roots of both sides. We'll move the constants around in the algebra. It gives us a V is the square root of 6250 minus 30s. That will let us easily draw a V of S diagram. And we learned something about how V relates to S in the first region. But the question asked us how let's see. Actually, what we can do is plug in the 1750 feet. That's where this region ends. And plugging in S equals 1750 right here, or right there, what we get is that the velocity at that point is 100 feet per second. So what we've learned is we did not slow down to 25 feet per second in the first region. So we must do that in the second region, so we proceed to the second region. Okay, and so our region where our position is between the 1750 and a final position where we would come to a stop. And our conditions in this region are at the beginning of that region, we just learned that our velocity is 100 feet per second. And we know that that region starts at 1750 feet. That was given in the initial problem statement. This again, we have a of S condition right here, minus 7.5. So we will stay with our ADS equal VDV. Again, we'll have VdV on this side with a starting velocity of 100 in this region, integrating to an indefinite v. And our minus 7.5 is the value of a times ds. And the at the point where v equal 100 feet per second, that was our position of 1750, integrating to an indefinite s. Integrating v dv gives us v squared over 2 with our limits. Integrating minus 7.5 s ds gives us minus 7.5 s with our limits. Plugging in the limits and doing a little bit of rearranging, we get v is equal to the square root of 36,250 minus 15s. And so we suspect that we do reach the slower speed of 25 feet per second in this region. So we'll plug in 25 feet per second right here, or right here, and solve for the value of s that makes that true. And the value of s that makes that true is 2375 feet. Oops, you can't see that. The value of s that makes that true is 2375 feet, is where we finally reach a velocity of 25 feet per second. Now, what we can do is plot this equation, and that, which is for the first region, and plot the second equation on the same graph. And what we have here is a v of s graph. Okay, a square root equation here as given, a square root equation here as given. We do have a continuity of velocity. That was our 100 velocity. If we look carefully, we may not have continuity of slope here. Okay, well, and we certainly don't have continuity of slope here because we have a jump in acceleration in our original acceleration graph. That's a discontinuity, so that's going to give us a discontinuity of slope here, which is a little bit hard to see. Now this is v of s. The original problem asked about producing an s of t graph. The author didn't do that in the solution, so I'm not going to do all of it, but let's talk about it a little bit. And so coming back to the first interval that we've already spent a little bit of time on, and we produced a v of s equation in that first integral. Given that we have v of s and we want s of t, then the natural thing to do would be, given the region of the equation sheet, v, s, and t would be this one, v equal ds dt. And so given that v equals ds dt, and we know v of s, what we'll do is we'll take dt to the left-hand side, and we'll set that equal to ds over v would come to the denominator, but let's write that in, since we know v of s, as the square root of 62,500 minus 30s, and then we can integrate both sides dt as t goes from 0 to some indeterminate t, and in that interval s is going to go from 0 now up to the 1750 point, but we're not ready to plug that in. We'll plug in an indeterminate s value here, and when we integrate this side, we're just going to get t. Evaluate from limits t to 0, so that would just be t. So we're going to get a t equals some function of s. And when we're done, we could invert that to produce an s is equal to some other function of time, maybe some g of time. And then we could plot that first function. And what we would have to do is figure out how far t goes. We'd have to plug in s equals 1750 to that equation and solve for the value of t that gets us to 1750. And so we would then plot a graph s of t. We would take the stopping time that we figure out for this first graph, and we would get some kind of curve, probably heading up. Who knows? Because we are certainly traveling forward. Okay, and then we do the same thing here. Given v of s, we would do an integral dt equals an integral ds over this v of s right here, and that would give us another equation. Plotting both equations, we would have an s of t graph. I'm not going to carry it any further. If you want to work out the rest of the math, you're certainly welcome to. And that ends the discussion on this problem.